Hi everyone, welcome to the EK Genetics channel. In this video, you're going to learn how to build ceRNA networks from scratch in the shortest possible time. So stay with me till the end if you want to master this fast and easy. Step 1. What are ceRNAs and why are they important? Let's first understand what ceRNAs are. ceRNAs, or competing endogenous RNAs, are transcripts, such as lncRNAs, mRNAs, and even circRNAs, that regulate each other by competing for shared microRNAs. In other words, they act like molecular sponges. A lncRNA can bind to a miRNA, preventing that miRNA from binding to its target mRNA. This indirect competition changes the expression level of mRNAs and can significantly influence cellular processes. Why should we care about ceRNA networks? Because this crosstalk is a key layer of post-transcriptional regulation. ceRNA networks can 1. Reveal how genes are co-regulated in health and disease. 2. Help us identify diagnostic and prognostic biomarkers. 3. Suggest new therapeutic targets, especially in cancers and other complex diseases. So understanding and building these networks is an essential step in systems biology and bioinformatics research. Nash to Step 2, quick overview of the workflow. Here's a quick overview of what we're going to do. 1. Collect gene expression data, mRNAs, cRNAs, miRNAs from RNA-seq or microarray experiments. 2. Identify differentially expressed genes using statistical methods in R, DESeq2, EdgeR, or Lemma. 3. Predict interactions using 2 approaches: correlation analysis based on your dataset, interaction databases like miRCode, TargetScan, and myRTarbase. 4. Clean and filter interactions to keep only those involving your DGs. Visualize the ceRNA network using R, iGraph, or Cytoscape. 6. Analyze the network to avoid overcrowded graphs and focus on meaningful connections. 7. Identify hub genes using centrality measures or machine learning methods, k-means, Cytoscape plugins. 8. Generate a refined network highlighting only the most important genes for better interpretation. Now let's go step by step. Step 3. Collecting data. You need gene expression data for mRNAs, lncRNAs, and miRNAs. These can come from RNA-seq or microarray experiments. Good news, you don't always need to analyze raw data like FASTQ files from scratch. In RNA-seq, databases like TCGA or processed datasets in Geo already provide you with ready-to-use expression matrices. These are normalized and aligned so you can use them directly. The same goes for microarray data. Most Geo or Array Express studies also share normalized expression matrices. But if you decide to work from scratch and analyze raw files yourself, for example, to apply custom filtering or advanced pipelines, you can download FASTQ files from the SRA, Sequence Read Archive database. In that case, you'll need to perform all steps, including quality control, alignment, and normalization. For most ceRNA network studies, however, using these publicly available processed matrices is perfectly fine and saves a lot of time. Important note, everything I explained here is for when you want to build your ceRNA network using a single dataset. If you want to combine multiple datasets and build a network from integrated data, you need to know how to perform meta-analysis of gene expression data to properly merge them. I'll explain meta-analysis in detail in another video. Step 4. Differential expression analysis. Now you have your gene expression matrix, whether you created it yourself by analyzing raw FASTQ files or downloaded a processed version. The next step is to identify differentially expressed genes. In R, there are 3 main packages you can use. 1. DESeq2 for RNA-seq count data. 2. EdgeR, also for RNA-seq count data, especially for small sample sizes. 3. Lemma, best for microarray data or for RNA-seq after transforming counts to log2 CPM, VOOM method. You'll filter your genes based on statistical criteria. For example, log2 fold change 1 Mach, adjusted p-value FDR 0.5. This step significantly reduces your data. For example, you might start with 50,000 genes, but after filtering, you could end up with only 3,000 significantly differentially expressed genes. These DEs, mRNAs, lncRNAs, and miRNAs, are the key players for your ceRNA network. Step 5. Predicting interactions. Now comes the key step, predicting lncRNA, mRNA, mRNA interactions. There are 2 main approaches you can use. 1. Correlation-based prediction. This method uses your own expression data to infer potential ceRNA relationships. You should calculate the Pearson or Spearman correlation coefficient for each RNA pair across all your samples. The biological expectation is important here. The correlation between lRNAs and mRNAs should be positive because when an RNA sponges a miRNA, the repression on the target mRNA is lifted, leading to increased mRNA expression. So, you'll typically keep pairs with a correlation coefficient higher than 0.4 and a p-value less than 0.05. The correlation between lncRNAs and miRNAs should be negative because as the lncRNA sponges the miRNA, the amount of free miRNA decreases. Here you keep pairs with correlations lower than magnitudes of 0.3 and significant p-values. The correlation between miRNAs and mRNAs should also be negative, since miRNAs generally suppress mRNA expression. Again, pairs with correlations lower than 0.3 are typically considered. Finally, only keep lRNA-mRNA pairs that share at least one common miRNA, which will be confirmed in the database-based step. Database-based prediction. The second approach is to use well-established databases that provide either experimentally validated or computationally predicted interactions. For LNC RNA-miRNA interactions, you can use miracle-predicted pairs or star-based ClipSeq-supported interactions. For miRNA-mRNA interactions, options include target scan, seed sequence prediction, MIR tarbase, experimentally validated target or DV machine learning predicted interactions, and star-based validated and predicted interactions. For circRNA mRNA interactions, if needed, circ-base and star-base are commonly used. How to download from these databases? It's straightforward. 1. Visit the official websites, e.g. dummerco.org, www.targetscan.org, starbase.cisu.edu.cn. 2. Go to the Download or Data section. Download the relevant files, such as LNC-RNA mRNA interactions from myRCode or validated myRNA target interactions from myRTarbase, usually in CSV or TXT format. Once downloaded, you need to clean and pre-process these files before moving to the next step. Step 6. Building and filtering the ceRNA network. At this stage, you have all the interaction files downloaded and cleaned, but data cleaning is critical before filtering. 1. Cleaning and standardizing the data. Remove interactions that are irrelevant or duplicated. Make sure the gene IDs match your DEG list. Many databases use different gene ID formats. For example, ensemble IDs in your dataset versus Entrées IDs in the database. You may need to convert them using ID conversion tools like Biomart in R or online converters. 2. Filtering the interactions. Keep only those interactions where all RNAs are in your DEG list. For example, if you have 3,000 DEGs after filtering, extract only the lRNA, miRNA, mRNA triplets where each component belongs to those DAGs. After this step, you'll have a refined set of interactions representing all possible ceRNA relationships among your differentially expressed genes. Step 7. Visualizing the network. Now it's time to visualize the network. You can draw the network directly in R using the iGraph package, or use Cytoscape, which is more user-friendly and offers many visualization options. But remember, this step is mainly for visualization. If you include all interactions, especially when you have hundreds or thousands of them, the network will often look too dense and messy to interpret. That's why we need the next step, identifying hub genes. Step 8, identifying hub genes. To focus on the most important genes in your ceRNA network, you can identify hub genes using different centrality measures. These measures show how central or important a node gene is within the network. Common centrality measures include degree, number of direct connections a gene has, betweenness, how often a gene lies on the shortest path between other genes, closeness, how close a gene is to all other nodes, eigenvector, influence of a gene based on the importance of its neighbors, PageRank, inspired by Google's PageRank, highlighting influential nodes, coreness, K-core analysis, how deeply a node is embedded in dense subnetworks. You can calculate all of these with the iGraph package in R, or use the network analysis section in Cytoscape, which can compute many of them automatically. Hash filtering hub genes. There are different strategies. 1. hard filtering. Select, for example, the top 10% of genes based on a centrality measure like degree or page rank. 2. Machine learning-based clustering. Use algorithms like k-means clustering to group genes based on multiple centrality measures. Determine the optimal number of clusters using the elbow method. Select the cluster with the highest centrality values as your hub gene cluster. 3. Cytoscape plugins. Plugins like CytoHubba or MCode can automatically rank and highlight hub genes. After this step, you'll have a much cleaner and more interpretable ceRNA network focused only on key hub genes, which makes visualization easier and biologically more meaningful. And that's it. Now you know exactly how to build a ceRNA network step by step, from raw data to identifying the most important hub genes. If you found this helpful, hit like, subscribe, and stay tuned for more bioinformatics tutorials here on EK Genetics. See you in the next video.